Okay. Hello, hello, hello. Um, hello. Thank you, Anthony. Okay. Hello. Hello, Anthony. Thank you. And hello, Vicky, for the double. I'm going to do this quick. And hello, Mafine. Hello, Victoria. Um, okay. I'm going to do this quickly. Yes. Thank you, Anthony. Hello, Vicky. Thank you. Good morning, Gabriel. Thank you. Hi, Melanie. Good afternoon, Fabia. Good afternoon, Caitlin. Good afternoon for the double Victoria. Good afternoon, Lachman. Hello, Muffin. Good afternoon, Bridget. Good afternoon, Roger. Good afternoon, Zoe. Um, wait, and I know there's more people. How do I do it? Sorry, sorry. Okay. Um, okay. I want to get down to business. Oh, sounds like someone's about to ask a question. Oh, hello, Lear. Okay. Hello.
Hey, good morning.
Good morning. Good morning. Okay, everybody. Um, so here's the story. We have two more classes today and Wednesday, right? Yes, good afternoon, Sonam. Thank you. And good afternoon, everybody. Okay. Um, I still have some more content I want to show you. Again, it's the most exciting content of all, I think. Any content I'm showing you today and Wednesday, I want you to follow. I want you to pay attention to. I want you to be prepared to answer questions about it on the final, but conceptually, okay? The last concepts of this course are the concepts that I think make everything worthwhile and put the prior concepts together. So I want you to follow the concepts that I'm going to be saying for the next 2 days. Um, you are responsible for them, but you should understand that I'll understand you're not expected to solve quantitative or intricate problems regarding these concepts. The last kind of problems that you would ever have to solve on the final would be like Gauss's law problems. Like, in other words, anything I've said past the Gauss's law homework is to be understood conceptually. You don't have to worry about it solving it quantitatively. Okay, that's number one. Number so number two, um, now at this point, I have to admit, there's still a couple of people that I owe exams to. I not that many, a couple, and for what it's worth, I mean, those people's exam. If you haven't gotten your exam back yet, you're among the few. It's still not personal. I apologize, and I'm rushing. I'm getting them to you, but yes, perhaps at this point, you may have been one of the truth is if you handed in the exam on time, then you've gotten it back by now. If you didn't hand it in on time, you might not have gotten it back by now. That's not a punishment. It's just a natural effect of sequencing. But most of you have gotten it back here, and all of you will by the time within the next couple of days, before you take the final. Uh, I wanted, as I was just saying a minute ago, I still want to cover the last concept for all of you all in the next couple of days so that you see why all of this is worth it. However, of course, you are concerned about your grades, and so am I. Of course, we have to balance between learning as much physics or liking as much physics as possible and doing as well as possible. Of course, I understand that and respect that. So I want to try to balance that. You, what I want to say is this. I want to get some facts about the final exam and final grades and final expectations sort of out of the way right now. Again, and if I sound frenetic, it's because I want to finish the course. I want you to be as calm and as strong as possible in finishing the course, and that is my investment as well. But forgive me if I go a little fast right now. Again, I'm going to remind you right now in the chat, I'm going to remind you of my cell phone number over the next couple of days or the next couple of weeks. If you have any kind of concrete question that can be texted to me, hold on. I'm just reminding you what I said on the first day of class. Uh, I can get back to texts fairly quickly, often more quickly than emails. I like texts when they are fast. If there's something you can ask me over by text, like, can I still give you a homework? Yes or no? Is this material on the final? Yes or no? Things like that. I'm happy to tell anything that can, or can I set up a phone appointment with you to discuss my midterm? Yes or no? Like, and then we make an appointment through the texting. Sure. Anything I can do to clarify things over the next 2 weeks, I'm happy to. Um, but so now I'm going to say a bunch. In other words, if you miss anything I'm about to say right now, wait, yeah. So what I hope is becoming increasingly apparent. I hope you saw in the Google Classroom this morning. Your final exam will be posted no later than 8 p.m. this Friday. It might be posted a little bit earlier, and you'll be notified, obviously, but no later than 8 p.m. this Friday. Then it'll be due Tuesday night by midnight of the next week, Tuesday the 20th. So you have all weekend and Monday and Tuesday to do it. Okay. I'll get you in one. Good. I'm glad there's questions. I'll get you in 1 second. Let me just say this before I forget. So it's just like the midterm. It's take home, open universe, same expectations for the most part that you can't, it's not good enough just to know answers. Of course, you have to show your work and show what you're doing like you did before. But you'll have from Friday, no later than 8 p.m. till Tuesday midnight to turn it back around to me. I want to say more about the content and the grading and the grades and all that. I will say in 1 second. But I know someone has their hand up. Just want to before I like forget what I was about to say. But yeah, I think. Okay, wait. Okay, wait. Okay, so things are happening in the chat, and well, first of all, I'm sorry, Melanie, you had a question, I think.
Yeah, I wanted to know more about the layout of the final
Oh,
exam. So, is the final exam the same layout like for last year's final exam? Like you would give us the option to redo one of our weaker.
okay. That
Okay.
yeah, no, perfect question. Yeah. I am totally about to get to that. Like, yes, that's about the content. Very fair question. I'm going to get to that in 1 second. I'm just trying right now for everybody. These are good questions, and this is the right time to ask them. Again, if I say something and then you miss it, please do text me because I also want to finish content. But yes, first I just want to make the timing clear. The time and the format. Like the format is take home and all of that. And the timing that I'm saying is no later than 8 p.m. Friday, due back Tuesday midnight. Now, someone in the direct, and I'm going to answer Melanie's question in a minute about content. Someone else in the direct chat, however, is about the timing, and they're asking very politely and very reasonably. They're asking, is there any possible way I can post a little bit earlier on Friday? Um, um, because they want more time to work on it. I totally respect that request. And I respect the fact, by the way, I know everybody has different religious observances and things like that. Like, I know some people can't work after Sunday on Friday or like during Saturday, and other people can't work on Sunday. Like, I totally get, and this is one of the reasons that I like just giving a take home that has like a whole bunch of days. So I don't think anybody can or will work every one of those days. This is not, anyway, I just want to make clear I fully respect, I mean, more than you know, the fact that people pray and are with families and things like that. And that should take priority over physics for a day or whatever. But I'm hoping in general, when I make these like 4 day things, that there's some section of time in there that can work for anybody and everybody. I also respect, by the way, that some people need a lot more time to do exams than others, but that's why I give, in effect, infinite time to everybody. Okay, that's a sidebar. That's not what but the real honest reality to the person who's asking, can't I post it earlier than 8 p.m.? Here is the most honest thing I can tell you is, honestly, I'm actually going to try to, yes. Honestly, I'd rather get it off my books before 8 p.m. and to you. And if I any earlier, I'm not going to wait till 8. I'm going to try my best to get it to you as early as possible. It might be significantly earlier than 8, but I'm just being honest and realistic that I have obviously fallen behind on a lot of things this semester and blah, 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 and I'm more tired from chemo than I thought I would be. So I just don't want to mislead you. I'm saying I will keep my promise that it won't be later than 8 p.m. I'm going to shoot for earlier than that. I'm going to shoot for a lot earlier than that, but I just can't promise that I will succeed. So that's my realistic answer but sure, I have no problem having you have more time. I just don't know if I'll be ready in time. Okay, that's because there's like four sections and blah blah blah. So that's on that. Okay, no problem. Yeah, no, and I do understand. People work on weekends. People have there's no perfect thing that's going to happen, but I am just trying. I try to give a big chunk so it sort of can overlap somewhere somehow with people. But the other thing is, to back to Melanie. Wait, wait. Well, wait. No, no. Okay, okay. Hold on. I'm not really. I'm doing my best, but I can't really renegotiate the whole structure right now because there's more things that happen in the direct chat. What one thing is, no, wait. I can't give it before you have lab. I don't. You have lab on. Wait, how do you have lab on? Oh, right. No, yeah. That I wait. Just to be clear, Thursday night is lab. It's a board. Wait. Hold on. Pause for a second. Who is your lab professor? Is it Walters or Tally? It's Walters. Okay, the one thing it's on Gauss's. Okay, one thing. All right, no, that is helpful information. I also, sort of have a duty to keep it fair among all the sections, and the sections have different lab professors but one thing, if you remind me, one thing I will do, I'm happy to reach because I think honestly, I will reach out to Professor Walters that about spending her Thursday night, your Thursday night reviewing and practicing and preparing for the final rather than doing a Gauss's Law board meeting. That I'm happy to offer. I just have to communicate with her. I mean, we often do that. And I don't want to slow down too much right now, but I'm glad you just brought that to my attention. No, I would rather you spend your last lab period with her with the practice documents preparing for the final. Now, I can't have you do that once the final's already distributed. That doesn't make any sense. But I mean, it's not fair to the other sections, et cetera, et cetera. It defeats but no, you can spend that lab period preparing for the final, which I'll get with the practice documents, which then also is the last thing I want to say about this logistics. Like, even if the actual document is not posted, until 8 p.m. Friday, you're going to know, you're going to have such a clear idea of what's possibly on it, like the possibilities for what's on it before then, that there's tons that you can do to get yourself together for. In other words, what I always advise with all of these exams is the format is such that you should write a rough draft out anyway first and then a final copy. Really, it's a much more productive thing to do that than some of you might still realize. So, absolutely, in the days leading up to Friday, including during lab period on Thursday, you can be basically already preparing this exam. You'll know mostly what's on it and stuff. And you can be getting your document together definitely before the actual thing is posted. But then once it's posted, then it's go time on finalization. So, I'm going to meet you halfway, is basically what I'm saying. And I do want to move on. I get what you're saying. And you can remind me, one of you can send me a text to remind me to talk to Professor Walters to shift the plan for Thursday night. That I'm happy to do. But I can't actually make the exam come out before you're preparing for it as a group Thursday night. Okay. Um, does that make, well, I hope that makes sense because that's what I can say about that. Maybe someone give me a thumbs up or something, just even if you don't like it, just tell me if it makes sense what I just said. Okay. All right. That's good enough for me. Okay. Thank you. Now, thank you, Vicky. I didn't see that. All right. Oh, thank you, other direct typing. Okay. Okay. And but I am serious. If one of you wants to send me a text later on, like not in the middle of class, just to remind me, please reach out to Professor Walters. I will do that happily. Now, the other thing is, this is back to Melanie's very fair question now. As far as what's on your exam, you will notice now in Google Classroom, or tell me if I'm wrong, but I think you should notice now in Google Classroom that there's been a practice exam posted for a while, like the final exam it's called like last year's final exam or something like that. That's been posted for a while. But now also as of this morning or something, I posted something that said the final exam from last semester. Now there is some overlap between those two documents. There is definitely overlap, but there are also some distinctions. What Melanie noticed, or what Melanie remembered from last semester, from 203 last semester, is quite correct. Like something I started last semester that I may or may not do with you, so bear with me for a second. What I did last semester is that one of the problems that you were required to do was a redo of your weakest problem from the midterm. Now that's partly because like I took so long. It's partly because that's a good thing to make your midterm a learning experience. So you have the opportunity to revise the draft and learn from it. And because you had to wait so long for it, like we should do something with it and not just have it be a kick to your head, especially if you got a score that you don't like after waiting this long or whatever. So it is true that last semester, one of the problems on the final last semester in both classes was redo your weakest problem from your midterm. And you had to submit the old version and you submitted the new version. Um, it is distinctly possible, it is possible to answer Melanie's question that I may do that again this time. It may be one of the required problems of your final, or it might be an optional problem, or it might not be there at all. Am I trying to keep you in the dark? No, I'm not trying to keep you in the dark. I haven't fully decided what's appropriate for this group and for this semester yet. I may give you more of an update on that on Wednesday, but I can tell you right now, when you want to prepare for this exam, for sure, you're going to do essentially two problems, just like you did in the midterm. There's going to be some kind of choice involved. It may be that one of the problems is required and the other one's a choice or something like that. And of the two problems you do, or of the choices you have, they will be pulled from those two documents that you now have available to you. In other words, the way I want you to prepare for this exam is be ready to answer any of the questions on either of those two documents. Like your exam will be created from those two documents. I cannot promise yet exactly in what combination, but if you have a lab preparation, if you have a lab period on Thursday where you prepare, like be ready to go with both of those documents. Be ready to redo a problem from your midterm. I may update you more on Wednesday as to whether that's definitely happening, but I may not. Like you should be prepared for that possibility. Um, if I do say redo a problem from the midterm, I mean, I think for some of you that's a good opportunity. You may welcome that, but just recognize that you literally have to do it. You have to redo the problem. You don't just like submit the parts where you got wrong before. You resubmit the whole problem. So it counts as a full problem. The other thing is that it's possible that you'll have a true false section. Like I think you see in at least one of the two documents that sometimes the final exam for Physics 204 has a choice of choosing a true false section rather than solving a whole problem. Now that's an unusual thing. That's not usually the way we test or learn in this class. I will tell you right now, because I'm going to shift gears in a minute. If you choose, or if we do that true false section, or if you choose it, it's totally a way of testing you on the concepts that we're doing right at the end of the course, so that you don't have to solve problems or anything on them. You just have to know these important concepts from the last 2 days. So I would suggest once I start talking about physics, like in a minute today, and when I'm talking about the physics on Wednesday, I would suggest that you have the true false out in front of you from the prior exam, like whatever that old exam is that I posted. Have it out as a way of taking notes or as a way of listening to me the next 2 days. It's not cheating. I'm encouraging you to do it. In some ways, of course, doing true false is a lot less work than solving a whole problem, but it's also a lot more risky. I'm sure you understand that. So it may be a choice. You may have a choice of just answering a bunch of true false questions about this conceptual content from the last week. Uh, but there is no partial credit there. For some of you, that's much better. That's a big relief, but it's also much riskier. So just bear that in mind. Anyway, what I'm trying to say to Melanie and to everybody, I want to get back to physics in a minute. But your final exam will be any combination of problems or choices from the two documents that have now been posted, the one from last semester and the one from last year. They overlap, but they're not the same. Um, oh, and sorry, one thing I will also, as a concession, I'm not trying to confuse people. I'm just trying to make it as clear as possible. I will tell you, I've gotten a number of comments in the background, not only from your MSRC tutors, but your lab professors and from some of you as students. It has come to my attention that these days, all that you do with circuits, you do all exclusively in the lab, and we never really talk about circuits much at all in the lecture. So I would, if you're trying to decide what to study and what to emphasize in the next couple of days, or what to start preparing, or how to use your time during Thursday night lab, yes, I think it's fair. You could make circuits your last priority. I mean, if you've done everything else and and you're really solid to go on everything, then make sure you know your circuits. But you can make circuits your last priority, and you can assume that one way or another, it'll be possible to avoid circuits on this exam. I'm not saying I might not make it a choice, but you won't. You'll be able to avoid circuits on the exam if you so choose, because I recognize we don't talk about them in lecture. Okay. Um, okay, I'm looking at okay, I'm looking at can you use so I'm about to go on, but there is one question in the chat. I think I understand. There's a question in the chat that says, can we use what we previously had? I think that person means if, and you should tell me, but I think that person means if you're choosing to redo a problem from the midterm, can you use the results from it that you actually got right? Yes, you can, but you still have to anything you got right, anything you got full credit, you can assume is right, and therefore you don't have to change it or fix it. But you absolutely still have to like rewrite it from like this. You'll give me a fresh new final. It's like an improvement. It's like a revised draft, kind of like what we were doing with homeworks early on before many of us, including me, fell behind. So in other words, if you right. So whichever problem you did worst on your midterm, you're going to resubmit that possibly from beginning to end. All the parts that were wrong, you have to do better and do differently. All the parts that were right, yeah, you can do them the same way again, but you still have to do them again. Does that make sense? Is that okay? Okay. So that's my answer to that. Great. Okay. Thank you. Okay. So are we? So again, I'm just trying to make clear. Your final exam will be taken in will be a combination of problems taken from the two documents that you see in Google Classroom. The final exam from last semester and the final exam from last year. I'm not yet promising in what combination how the problems will be put together. It's possible you'll redo something from the midterm. It's probable, but it's not definite. It's possible that will be an obligation. It's possible that it'll be a choice. I'm not sure. Same thing about true false. There will probably be a true false section on your exam that will possibly be a choice. Um, and to the extent that circuits are on your exam, you'll be able to choose your way out of them if that's what you so choose. Okay, is that so? That's what I'm basically saying now. And remind me, I will arrange it so that your lab section on Thursday is review for the final. Okay. That said, I want to go on with physics content. I'm going to be a little fast. I'm going to talk a little fast, but it's going to be, again, conceptual. How do you prepare the content that I'm talking about? You might listen closely, take notes, but maybe even have one of the true false documents out in front of you to get a sense of what you're looking for while you listen to me talk about this content. Okay? So I'm going to go. Okay. Here's my goal is to get to these three equations, believe it or not, today and Wednesday. But I'm going to split. Okay, that's where I'm trying to get to. I haven't said them yet. The very last thing, what I've said so far as of last Wednesday, Okay. The main the main takeaway from last Wednesday is that whereas every bit of existing static charge, every bit of charge that exists creates electric field lines that burst out radially from the point charge, right? Every point source of electrical charge, if it just exists, if it's just sitting around, it creates field lines that radiate out in all directions. Um, Mag magnetism is caused by moving charges. So every bit of moving charge, every charge with velocity, or in other words, every bit of current, right, is not a scalar point, but rather a one-dimensional vector. Like currents are flow, are lines of charge that have direction. They create they create magnetism, they create magnetic field. But because they are already vectors, since a moving charge, a charge with velocity is already a vector, then the kind of field line it creates is a cross product of, of two vectors rather than the multiplication of a scalar by a vector. So magnetic field lines are always perpendicular to not only the flow that created them, but the displacement from that flow. That's what the first statement is really trying to say. It's a magnetic field is a cross product of moving charge with the displacement vector from the moving charge. So magnetic field lines loop around currents. That's the main thing I'm trying to say in English. Like if you have a line of current going across the page like this, then the magnetic field lines will not burst out like radii from that line, or they will not burst out like spokes. They will loop around the line. The magnetic field lines will be concentric circles getting farther and farther away from a line of charge. And the magnetic forces that these lines exert are at right angles to the lines themselves. Like, in other words, another cross product. So a line of charge here will cause a magnetic field above it, like like a line of charge, a line of current here will cause magnetic field above it to come out of the page, in front of it to come down the page, below it to go into the page, and behind it to go up the page. The magnetic field line will be a circle around it, and circles getting farther and farther apart. Less and less dense as you get farther away. If you're underneath a line of current, you'll experience a magnetic field going into the page. Now, if you're just a mass sitting around in a magnetic field, you don't care. Magnetic fields don't affect masses. If you're just a charge sitting around in a magnetic field, you don't care. Magnetic fields don't exert forces on sitting charges. But if you yourself are a moving charge, if you are a current in a magnetic field, then the magnetic field will exert a force on you that is the cross product of your velocity with the magnetic field. Another cross product, in other words. And so if you are a wire down here, a current below the top, if you're down here in a magnetic field going like this, that's another cross product. You would take your right hand, put your fingers along the velocity, curl into the magnetic field that's going this way, and your thumb would point up, i.e., you'll be pulled up to that top wire. So magnetism accounts for the fact that two current carrying wires do attract to each other, but it accounts for it through this thing called a magnetic field. But the magnetic field, if there's anything I'm trying to say right now in English, it's that magnetic field lines are not infinite lines that go from sources to sinks. They are closed lines that go round and round. They don't have beginnings or ends. They loop around lengths of current. That's what I'm saying right now. And it's because it's all because of these cross products, but the cross products are because what is causing magnetism is not a scalar point of charge, but rather a vector of moving charge. Right from the get-go, the thing causing magnetism has direction. Okay, so okay. So, oh, sorry. Sorry. Okay. Oh, and thank you. Did I even mention? Thank you. Sorry. Okay, intro. I mean, something in the direct chat that is important. Um, I don't even remember if I mentioned last time, but please tell me but the course evals, you get points for doing the course evals. They're actually really important. I don't mean to sidetrack myself. Thank you for noticing that the course evals are in. Wait, could someone just? Well, it doesn't matter. I don't remember if I talked about them or not. Um, Sorry. I don't remember if I talked about them or not, but they are really important more than you know. They serve a whole different function from ratemyprofessor.com, which I understand everybody takes very seriously. That provides one function. This provides another function. They are really important. You get points if you do them for this class. You technically you're supposed to do two forms, one for the lecture and one for the recitation, even though they're the same. You could say the exact same thing, but it is two different sets of data. But yes, right now, there's a silly thing that if you're not a John Jay student, you don't have a John Jay email, you can't even log in and do them, which is ridiculous. And we're trying to change that. Believe me, it doesn't make any sense, but it is the case. So I'm just answering a question in a direct chat. I'm asking everybody, please do the course evals. You get 20 points if you just provide proof that you did them. Don't provide, I won't see yours. I don't want to see. I will never know who fills out what individual information. I promise you. I don't want to, and I can't. Um, but if you just provide a screenshot of proof that you did it, you'll get 20 points if you did both. But for those of you who are not John Jay students, because that's the question in the chat, uh, just put in the portal. I tried, but I'm a John Jay student. It won't let me, and I will give you the points for trying. Honestly, because it's ridiculous that you can't. It's not your fault. Um, okay, so just remind me in the portal. Just say I'm not. Maybe even tell me what school you're coming from so that I can be happy about that to welcome you. Whatever. But okay, but no, there isn't an alternative. Not yet. Look, honestly, I'm even on the committee for that. And I've brought it to their attention that this happens every semester, that it's ridiculous. And we are trying to change it for the future, but I don't think we got it changed in time for this semester. So there's an alternate way you can get the points for my class. Don't worry about that. Just write that you come from Brooklyn College or whatever, and I will give you the points. Um, but there isn't an alternate way that you can fill out the form. I apologize. Wait, sorry. Oh, okay, thank you. Sorry. Wait, so I'm not in the building today. I'm always in the building on Tuesdays. I'll be in the 11 to like 12:30. Like I'll be in my office at 11 tomorrow morning. If but okay, wait. Sorry, I have to get back, but I will be there tomorrow. Tuesday, 11. Um, uh, okay, sorry. Okay. So we now have a law that dictates what the magnetic field is caused in the elemental case by a small amount of moving charge. That's just like Coulomb's law for the electrostatic field from a static bit of charge. Well, what happened in this class and in the study of physics after we got Coulomb's law for a bit of charge, we we then thought, well, okay, but how can we get more realistic? What if we have a continuous distribution of charge, like a line or a sphere or something like that? What do we do for continuous sums of charges? And we moved from the concept of field to the concept of flux, and we developed this thing called Gauss's law in order to figure out in order to figure out electrostatic field at a point in space over here due to some bunch of charges over there. And you do need to know that for the final and everything, Gauss's law, like you're responsible for, right? Well, the question is, now that we're talking about magnetism, can we, if what if we have a bunch of currents? Is there a way that we don't have to like add up all these cross products? Can we use some concept of flux or something like that? Can we apply some kind of Gauss's law to magnetism in order to find out the magnetic field over here due to a bunch of currents over there? Like that's my question. I'm not asking you. I'm saying that's the next like rhetorical question that occurs in physics. But here's the deal. What happened? Well, we consider the net flux through, we consider the net magnetic flux through a closed surface, which is what we were doing with Gauss's law for electron, right? And what we find is the total amount of flux of magnetic flux through any out of any closed surface, the net amount of magnetic field lines coming out of a closed surface, remembering that out we consider positive and in we consider negative, the net amount of magnetic field lines coming out of any closed surface turns out to always be zero, because magnetic field lines are all closed loops themselves, are already closed paths. In other words, any magnetic, if you take a container anywhere in space, like we were doing with Gauss's law, if you consider a container anywhere in space and start counting the number of magnetic field lines that come out of that container because of like some currents that are inside the container, let's say, right? If you start counting the magnetic field lines that come out of the container, you may find a bunch. There might be a bunch of currents inside. But unlike with electrical field lines, any magnetic field line that comes out of the container will necessarily somewhere come back into the container because every magnetic field line is already a closed path. Unlike electrostatic lines, which just burst out from positives and sink into negatives or go on to infinity. Magnetic field lines don't go on to infinity. They always come back and connect with themselves. Why? Because of that because they're always following the right-hand rule, the cross products. And why are they always following the cross products? Because, okay, fair enough. I hear you, direct check. Fine. Thank you for that. Okay. Why? Again, because magnetic field lines are not caused by points. They're caused by vectors. So again, I'm saying the magnetic flux, the English way of putting this, what people say in physics, the meaning of this law. Oh, and so this is Gauss's law for magnetism always has zero on the right side. A way of saying that in English is there's no such thing as a magnetic monopole. There's no one item from which magnetic lines emanate. The way there is for electricity, there's a such thing as an electric monopole. What? A proton is a positive monopole. An electron is a negative monopole. It's one pole. It's one object that if you put it on the table, the lines burst out of that object. There is no microscopically, elementally, there is no one bit of matter that if you put it on the table, magnetic lines come out of it. You might say, what about a big hunk of iron? But that's a big hunk of, I mean, a hunk of iron is a macroscopic object that's made up of lots and lots of little elements. There's no element in there that is making magnetic lines burst out of it. The only thing that makes magnetic lines are currents, are flows, rivers of flowing charge. That's what makes magnetism. And the magnetism circles around the flow of charge. So magnetic lines are always, again, this is all just really quickly. The whole idea of all of this is symmetry and asymmetry. Like, like, remember we've been saying that field lines in general are only as asymmetric as the thing that produces them. If you make a dot, it I mean, if you have a dot, it makes lines that burst out symmetrically in all directions. If you have if you have a line of static charge, it makes lines burst out in all spokes directions, like in all directions except that one. If you have, wait, hold on. Wait, okay, let me, well, okay, I'll get that in a second, but um, um, sorry, wait, I'm going to hold that question for a second. Sorry, um, it's a good question. Uh, but what, okay, wait, sorry. Um, what I'm trying to say is that field lines are always picking up on the asymmetry of the thing that causes them. So if you have a flow of charge, a current going in one direction, right? It's going to cause magnetic field lines that are as symmetric as possible, given that you've now picked off an axis of space and called it special, and picked off a direction in space and called it special. The most symmetric, simple way to convey to all of space that there's a current going in a certain direction along a certain axis is for there to be loops going around that axis. Like if the axis is going like this, if the current's going like the way my thumb is, then the lines of magnetic field curl around in the manner of my fingers. Now, someone's asking in the direct chat, how does this take into account attraction and repulsion? Yeah, great question. Everything I'm saying right now is assuming positive charge. If positive charge were if negative charge were going that way, that's the same thing as positive charge going the other way. So the lines would go the other way. So it's absolutely still true that if you have two lines of current that are both the same direction, they will attract. Whereas if one of the lines of current is flipped around the other way, it'll repel. Like attraction and repulsion are still part of this. They are responding to direction now, is what I'm saying. Direction of flow, not just only type of charge. Direction of charge flow, not just type of charge. I don't know if that answers that question or not. I mean, it's a good question. I think I answered, but I'm going to keep going. What I'm saying right now is that there's no singular object, elemental object that creates magnetism. What creates magnetism is objects with motion, objects with a velocity vector, charges with a velocity vector, i.e. currents. So we can't use the idea of flux through a closed surface to figure out anything about the magnetic field. Like I'm not, so this is a law that the magnetic flux through any closed surface always equals zero. It's a law. It's as important as Gauss's law for electrostatics. It's as important as a description of magnetism, but it doesn't help us compute anything. So instead, Okay. What I'm saying here is we're trying to, if my goal were to try to figure out what the magnetic field is over here due to some bunch of currents over there, I was hoping I could use Gauss's law. I was hoping I could look at closed surfaces the way I did for electrostatics, but that that doesn't help. That doesn't work in the end because if I look at the, well, I'll remind you, reminder of Gauss's law. Okay. Gauss's law said that you look at any closed surface and the total number of E field lines coming out of that closed surface, the total amount of electrostatic flux emerging from that closed surface is fully determined by the charge inside that, the charge enclosed within that surface. We were hoping to say some, oh, and let me remind you again, Gauss's law, the left side, do I want to say this right now? You may want to write this. I'm going to say, I may write it down for you again. I've said it before. You may want to write it again right now. Remember, well, notice that Gauss's law, the left side of it is like two-dimensional in nature. The right side of it is three-dimensional in nature. The, the, the background implication of this law is a closed, please write this down, a closed two-dimensional region of space is the boundary for a unique three-dimensional region of space, right? Like what Gauss's law, I'll say it again, a closed two-dimensional region of space is the boundary for a unique three-dimensional region of space. A closed area bounds a unique volume, is what I'm saying. And that's what Gauss's law is sort of assuming about space or geometry. It's saying, look, if you pick any container in the world and you want to know how many lines of field are busting out of that container, it's going to be fully determined by how much charge you find within the unambiguous volume within that container. The number of field lines coming out of a closed surface is fully determined by the charge found enclosed within that surface. I mean, in some ways, if you say it over and over again and you really and you think about it like water or something, in some ways it's almost obvious. I mean, nothing is obvious in physics, but it almost seems like it's obvious if you were talking about water. The total amount coming out of the boundary is fully determined by whatever's inside that boundary, right? So a closed two-dimensional region of space bounds a unique three-dimensional region of space is what's going on with Gauss's law. Now, we tried to make a law like that, or Gauss tried to make a law like that for magnetism. And the problem is that what you get on the right side every single time is zero because all the magnetic lines are already closed. So, so what Ampere said was, oh, okay, well, if that's the problem, if the problem is every magnetic line that goes out of the surface necessarily comes back in because the magnetic lines are already closed, why don't we just follow the lines themselves? Why don't we do this? Why don't we say, why don't we conjecture, and then he verified that the total amount of magnetic field around any closed path, L stands for like length, like L is the same as X or R or anything else. It's a one-dimensional, like notice this integral is now a one-dimensional closed integral. Ampere is saying, look, just follow any line in space and walk around any path you wish so that you get back to where you started, what you'll find is the total amount of magnetic field that you add up along that whole path is fully determined by the current enclosed by that path. Like, in other words, if you look at it, I'm trying to tell you that the law that we use to compute magnetic field is modeled after the Gauss's law for electrostatics. It has the same character, but it's brought down by one dimension on each side. So I guess I'll say this. I am writing it down. Okay. So here I'm saying Ampere's law is the same character as Gauss's law, and it's the same type of setup. You have a closed integral of the field on the left side, and on the right side you have the constant, and you have the thing that's causing the field being referenced. Like, right, charge causes electrostatic field, current causes magnetic field. So here we're bringing the whole concept down by one dimension, though. Here we're saying if you walk around any closed path in space, the total amount of magnetic field that you'll find adding up all around the closed path will be fully determined will be fully determined by the current enclosed by that path. It's just like saying the total number of the total amount of flux through a closed surface is equal to the charge enclosed by that surface. Only now we're bringing it down a dimension. We're saying any closed path is the boundary for an open area. Remember, open and closed means a closed region of space means one where if you walk far enough, if you walk far enough in the same direction, you'll eventually end up where you started. That's what closed means, right? It can apply to like a ring is a closed line segment. A ring is closed, a line segment is open, right? If you keep walking around a ring, you never have to turn around. You'll eventually get back to yourself. Same thing with the surface area of a globe, the skin of an orange. That is closed because if you keep walking on a skin of an orange, you'll eventually end up where you started without ever having to turn around, right? So paths can be closed or open. Surfaces can be closed or open. A piece of paper is an open area. If you crumple it up and touch all of its ends together, then it becomes a closed piece of paper. We're saying here a closed path is the boundary to an open area, just like a closed surface is the boundary to unique volume. That's what we're saying. And Ampere is saying, well, let's look at that, the the one dimension, two dimension relationship. Instead of the two-dimension, three-dimension relationship, let's bring it down a dimension if we want to look at magnetism. And it works. It turns out to be correct. One thing. So what we mean here by current enclosed, now remember again, with Gauss's law, charge enclosed meant all the charge that you find within that unique volume bound by the closed surface. Like charge enclosed meant all the charge inside the container that you were looking at. And it was sort of clearer because we live in three-dimensional space. Once you define a container, once you have a closed surface, there's clear one and only one volume inside that closed surface. I don't know whether the volume is open or closed because I can't see the fourth dimension of space. I mean, that's sort of a digression, but sort of not. Like when you close up a region of space, you go into the next higher dimension. Like here's a line segment. If I close it up and make it a ring, I can't do that without there being a second dimension of space to work within, right? So once you have a volume, I don't know whether a volume is open or closed because for it to be closed, I'd have to see it like bend in the fourth dimension. I don't have access to the fourth dimension. I'm not saying it doesn't exist, but I don't have access to it. So there's no, so the volume inside a container is just unambiguous, unique, clear volume. But now I'm saying I'm Ampere's law. What Ampere's law is saying is if you imagine a circle, right, in space somewhere, and you ask what's the B field, like what's the total amount of B field going around that whole circle? What Ampere's law is saying is, okay, that circle is a closed path. It is the boundary to some open area, like the disk within the closed path, right? Like the closed path is like a circumference, and it's the boundary of a disk within that circumference. Just like the rind of an orange is the boundary to the orange itself, right? So if you look at some closed path, it bounds an open area inside it. An open area, right? Not a closed surface, but an open area. Um, like a disk is open, like a piece of paper is open. It might not seem that way, but it is, because it's not closed. All right, anyway, the so a closed path is the boundary for some open area. Any current that is going perpendicularly through that area, any current that is flowing at 90 degrees to that area is what we mean by the current enclosed. So by current enclosed, what we really mean is current passing through the area that is enclosed. Okay, so that's Ampere's law. I just want you to understand that conceptually. I want you to see the connection between that and Gauss's law. Now we still have 14 minutes. There's one last thing I want to do today, believe it or not. So far we have Gauss's law for electricity or electrostatics. Gauss's. I'm looking at the chat too. Yes, yes. Right. Good. Yes, that picture that you got from the web or wherever you got that picture. Yes. Thank you. Oh, it's in the direct chat. People can't see it. Can I I'm not gonna copy your name, but I'm gonna copy. That is good. Hold on, let me see if I can just quickly put this in the chat for everybody. It's good. Thank you. And you should submit for points for this. If I can't, oh, yeah, okay. Yeah, so someone just in the direct chat. That's good. Like, in other words, the circles of our magnetic field line and they are fully determined by the current that's going through the area um, bounded by each of those circles. Yes. Okay, so that's three laws we now have about electricity. There's one last. Okay. Given all the above, then, a famous scientist who was actually a high school chemistry teacher named Michael Faraday, who gave us a huge amount of understanding about magnetic field lines and about magnetism, magnetic field lines, magnetic flux, the whole concept of flux in many ways, certainly magnetic flux, comes from this famous Scottish scientist named Michael Faraday in the early 1800s. And the good news about Michael Faraday is he hated math as much as some of you might. Like he did not like doing equations and solving problems, stuff like that. He liked to think of things very conceptually and visually. And that's the way we're ending this course. Again, everything I'm saying now, I'm saying a little bit quickly, and I want you to know it and I want you to appreciate it. But I want you to know it conceptually and visually the way Faraday did. You don't have to worry about grinding too many solutions. But what Faraday set this up, set up the following. Okay. Faraday, well, okay. Faraday said, wait, what if we take a constant magnetic field and just create it in the lab? We constant magnetic field. So this is like a bird's eye view. You might want to write this as a bird's eye view. So we got magnetic field, let's say constant magnetic field, all pointing, those are all X's. So all pointing into the page. And then let's take a bunch of metal rails and connect them together. So metal rail, then metal rail with like a resistor on it, metal rail, and we put a metal rod on the rails. And we push the metal rod along the rails at a constant velocity v, a constant rod, I mean, a rod of length L. So Faraday says, what if you've got a rod moving at velocity v through the magnetic field? Well, I mean, when it's not moving, there are a bunch of protons in the rod and there's a bunch of electrons. They're there, but they're not moving. So even though they're sitting in a magnetic field, they don't care. But once you move the rod at constant v, they're moving through the field, right? And remember, we said that if there's moving charges in a magnetic field, they will experience a magnetic force according to the cross product. Do the right hand rule. We've got charges moving to the left in a field that's pointing into the page. So any positive charges in the rod will be pulled down, like according to my thumb. Faraday predicted and verified that if you move this rod across a magnetic field, the magnetic field will create a magnetic force exerted onto the moving charges. According to the cross product, the positive charges at the top of the rod will start moving down the rod, and the negative ones at the bottom will start moving up. So you'll get current flow automatically through this closed, like since all the metal is attached, this is all metal and it's all attached. By moving the rod, you'll start getting current, which is very exciting because there's no battery here at all. Okay, this is called okay, this is very exciting, and you've heard of this before. This is called electromagnetic induction. What's going to happen is suddenly you're going to have electricity here. You're going to have like current going through the resistor, through the whole metal loop. You'll have I times R, like you have in the lab, current times resistance, which means electric potential. Like you'll have voltage, you'll have a totally working circuit here, except that it came into existence without any battery, without any chemical, without any voltaic cell at all. All you had to do was move the rod through a magnetic field, and now you have electricity, right? This is called electromagnetic induction. It is a change in magnetism inducing an electric current, an electric potential. As many of you may know, this is the beginning of the Industrial Revolution. Like, this is a generator. We generate electricity here without even having an electrical source, without having a chemical source, without having a battery. This is a generator. And literally, it is the beginning of the Industrial Revolution. It has huge practical implications. But the thing that I want to say about it, and I'm going to close with, I know we have 4 minutes, but only 4 minutes. I want to close with this. In this, he set it up because it originally makes sense. Like everything we've now understand, once we understand the magnetic field and that the magnetic field will cause magnetic forces to be exerted on, let me start that again. Magnetic field is caused by currents. The magnetic field only acts on currents, just like electricity is caused by charges, it only acts on charges. Gravity is caused by masses, only acts on masses. Magnetic field is caused by currents and acts on currents, but it acts in this funny right-hand rule way. So because of Faraday's cleverness, we can set up an apparatus where if you move a bunch of charges one way through a magnetic field that's pointing the other way, you suddenly get a magnetic force in the third way, and you'll now have electrical currents occurring without any battery, right? But it makes sense because of the laws that we already have from magnetism and electricity. The thing that's crazy about this with 3 minutes left, well, the apparatus that he did, the generator that he made, was an outgrowth of the laws that we just talked about, the laws that lead up to it. It makes sense. Like it's really clever, but it's not a surprise. But Faraday, who was very visual and liked to think in terms of flux rather than field, because he liked to be able to count field lines. He thought of this in terms of flux, and he said, well, what's happening here? What's happening here is the total flux through this rectangle of metal. The total flux is changing because even though the magnetic field isn't changing its strength, the area is changing. He thought, aha, we're getting less and less flux through this area, through this open area bound by the metal. And he said, I could think of this way, I could think of it as the change in magnetic flux through this open area is inducing electricity in the closed path bounding this area, he said, and which is a perfectly reasonable way to talk about it. You may want to, you may not want to talk about it that way. But the crazy thing is that once he said it that way, it turned out to be generalizable as a law for all other apparatuses that couldn't be explained. In other words, it makes a new and final law that I'm going to leave you with. We have 1 minute. I'm just going to write it. What Faraday's law is that the electric field in any closed path is equal to the change in time of the magnetic flux through the open area bound by that path. And so it's like what I just said about Ampere's law, but it's like in the reverse direction. I'm saying if you change magnetic flux through an open area, you'll get electricity in the path, in the closed path bounding that area. And apparently this is, well, it is. It is true even if you don't change the area, you just change the magnetic field through the area, this you'll get electricity. Or if you move the whole apparatus past the field, you'll get this electricity. If you ever change the magnetic flux, so again, this has this 1D, 2D quality just like Ampere's law, but it's in the reverse direction. Okay, I'll leave it. So I'll leave it at that. But we now have two laws that are 2-dimension, 3-dimension, and two laws that are 1-dimension, 2-dimension, and that's enough for today. So I'll see you in 2 days. If you have more questions about the final or anything like that, text me. Text me to remind me to talk to Ms. Walter, Professor Walters. Okay, bye. Have a good. Thank you. Thank you. Have a great day. Yes. Thank you.